Hey everybody, Mr. Mack here. Today I'm going to do this warm-up for 7.5 and go through some of the practice solutions for part 2 here, which we're discussing angle of elevation and depression. Okay, so we've got Mack is standing at the edge on the top of an apartment building. Mack measures the angle of elevation from his eye to the top of the building to be an angle of 56 degrees. Okay, so he is looking from his eye to the top of the building, and that angle is 56. We measure angles of elevation as well as depression always from the horizon. So the first thing we need to do before we put any angles is make the horizon line here. So here's the horizon, and the angle goes from the horizon up to the terminal side looking at the top of the building, and that angle is 56 degrees. Mack measured the angle of depression from his eye to the base of the same building at an angle of 47. Okay, so for angle of depression, same thing. We go from the horizon looking down. So this angle is 47. By the way, this is not to scale at all. So we see that this angle looks bigger than the 56, but that's okay. If Mack stands 5 feet tall at eye level, okay, so he is 5 feet, so he's standing on top of this building and his eye is 5 feet above the building. And the two buildings are 66 feet apart. So this length right here of this horizontal segment is 66 feet. How tall is the building across the street from Mack? How tall is the building he's standing on? Round to the nearest foot. Okay, so we are looking for height. Of the building across the street. Maybe call this height T for the tall building. And we're also looking for the height of the building he's standing on. So maybe I'll call this height small, or height tall, height small. Okay, H sub S. Okay, so the height of the tall building, I hope you see, is going to be, let's get a different color here. It's going to be these two legs added together. We don't know the length of those two legs. How about we call this one X and we call this one Y, and we know that horizontal segments and vertical segments are perpendicular. Of course, we're assuming that the building is vertical, and I think that's a good assumption. So we have this yellow right triangle and this orange right triangle, and we know an angle, and we know this side adjacent to the angle is 66 feet, and we are trying to find the side that's opposite. So X is the opposite leg, and the 66 feet is the adjacent leg. We also see this in the orange triangle, the 47 degrees, the X, or let's call this Y actually. I meant to call that Y, so this is Y. And I want to have the same variable labeled in two different places. So this is the opposite leg, and the 66 feet is still the adjacent. So we know that sine of an angle, just call it A, is the opposite leg over the hypotenuse. We know the cosine of an angle is the adjacent leg over the hypotenuse, and that tangent of an angle equals the opposite leg over the adjacent leg. And we remember this with SOHCAHTOA. And in this problem, it's the tangent that's going to be applied for both the triangles. So we can say, okay, tangent of angle, let's do the 56-degree angle first, equals the opposite leg, we're calling x, over the adjacent leg, which is 66. Let's zoom in on that. So we need to multiply the 66 to both sides of the equation to solve for x, because 66 is dividing, so we undo dividing by multiplying. And then we're going to go to our calculator. And so our calculator here, we've got 66, I'm using the Web 2.0 calculator online, times the tangent, here it is here, tangent of 56 degrees equals 97.8. So we're rounding this to the nearest whole. So what did I say? 97.8. 97.8. And this is going to be feet. Okay. The other equation here, we've got tangent of 47 degrees equals the opposite leg, which is y, over the adjacent, which is 66. And again, 66 is dividing. I want to undo divide. I'm going to multiply 66 to both sides. And then we're going to put this, we're ready to put this in the calculator because y is by itself. So we're going to do 66 times tangent of 47. 70.8 feet. Okay, so the height of the large triangle, or the height of the tall building is going to be x plus y. Goodness, I can't write. Been a long day. So the height is going to be 97.8 plus 70.8. 97.8 plus 70.8. One 168.6, 168.6, and I said round to the nearest foot, so 169. So the height is 169 feet, height of the tall building. Okay, the small building is going to be whatever the y distance that we already calculated that goes from his eye to the ground, subtracting max height. So the height of the small building here is just going to be y minus 5. So our y was 70.8 minus 5, and that is 65.8, rounded to the nearest foot is 66 feet. Okay. All right, I hope all that makes sense, and I don't know why there's a monster here. That was for fun. All right. So let's take a look at some practice here. Camilla is in the bell tower looking down at the old water fountain in front of Old Main. She knows the fountain is 175 feet from the base of the tower to the fountain. The old water fountain. Oh yeah, that's, know that. Well, I wrote the problem. I should know it. So here's the bell tower. And she's in the bell tower somewhere, right? So she's right here in a window maybe. Flat face. And the old fountain is over here somewhere, let's say. And she is looking down at it. Okay. And she says she knows the fountain is 175 feet from the base. So 175 feet is this length here. Okay, and so I got to be careful about this next part. The angle of depression from Camellia to the fountain is 25 degrees. So it's easy to make this angle the 25, and that a lot of students do that. But the angle of depression is always measured from the horizontal. So this is the horizontal here, and she's looking down from the horizontal. So this angle here is 25 degrees. Well, the ground is also horizontal. So we know that this segment is going to be parallel with this line. So that makes these two angles here alternate interior angles. And alternate interior angles are congruent. So this is 25. We also know, we could say, oh, well, this is a vertical line, the bell tower, and this is horizontal. So these two angles here have to be complementary, which means they add up to 90. So we could say 90 minus 25, and we would discover that this is 65 degrees. And we also know that this angle is a right angle, assuming that this is vertical and the ground's horizontal. So we have a lot of information here. We are trying to find how high is she in the bell tower. We're trying to find this height right here, all the way up to this point. So really all the way up to there. And so we have two angles to work with. I'm going to work with the 25-degree angle. We could do this one as well, but I'm going to stick with this one. So I'm looking at how does H relate to the 25? Well, it's the leg that is opposite. And how does the 175-foot segment on the triangle relate to this angle? It is the adjacent leg. This is the hypotenuse, which we're not going to use in this problem because we see this is another tangent problem. Tangent equals the opposite leg over the adjacent leg. And we have the angle. We're calling the opposite H, and the adjacent is 175. So we're dividing 175 into H, and we want to isolate it. So we are going to undo divide by multiplying to both sides. The 175 cancels. H is now by itself, and we go to our calculator, and we do 175 times tangent of 25. 81.6. And no I didn't say how to round, so let's just leave it to the nearest tenth, 81.6, and that would be feet. Okay. All right, another one. Rachel was admiring the statue of Captain Mack, a famous swashbuckling pirate. She's curious how tall the statue is. The angle of elevation from her eye is 20 degrees. Okay, so let's assume angle of elevation from her eye to the very top of the statue. Notice I'm starting from the horizon, and this is 20 degrees. Okay, so Captain Mack, assuming that its statue standing vertically, and it makes a 90 with the ground, and the 90 with Rachel's horizontal. She is 4 feet 8 inches tall. 4 feet 8 inches. And she's 30 feet from the statue. So this length, well, she know on the ground is 30 feet, but we also know that this length on this triangle, this horizontal, is also 30 because we're assuming this is making a rectangle. Okay, and we're looking for the total height here. Okay, so the height of the statue from the ground is going to be the height of this leg on this triangle plus this segment, which is going to be the same as Rachel's height. Now, I don't really like a mixed unit here. Let's put this all in feet. I know 8 inches can convert into feet by multiplying a unit conversion by 1 foot over 12 inches. And then the inches cancel. And 8 divided by 12, well, we know a 4 comes out of both, right? So 4 out of both, that would give us 2/3. It'd be 2/3, or about 0.66 repeating, right? So we can call this 4.67 feet. How about that? And this length is 4.67. So we need to find, let's call this leg X, and this is the opposite leg. And the 20 feet is, or the 30 rather, is the adjacent. So again, we're looking at tangent. And I'll tell you that tangent is a very common function used in a lot of practical applications, because horizontal lengths and vertical lengths are quite common to be given. So we have the angle is 20, the opposite leg is X, and the adjacent is 30. How do we solve for X? Multiply 30 to both sides. Go to our calculator. Times tangent of 20, 10.92, 10.9, 10.9 feet. So the height is going to be 10.9 feet plus 4. Let's say now just 7 feet. And that's going to be 4, so 9 and 7 is 16. So that's going to give us 15.6 feet. So the height of the statue is 15.6 feet. Okay. All right, number 3. I don't know why I have this warm-up thing right here. Let's get rid of it. A submarine is on the surface of the ocean preparing to dive. If the submarine dives continuously at an angle of depression of 13 degrees, How deep will the submarine be if it moves a distance of 1 kilometer along that diving plane? How will it go horizontally? Okay. So here's our submarine. It's going to dive at an angle of 13 degrees. Okay, so this is horizontal. I'm going to just draw the horizontal. That's horizontal. And here's 13-degree angle of depression right here from the horizontal going down. And it says it's going to move a kilometer along that diving plane. So the diving plane is this line right here that I've made. And it's 1 kilometer. 1 kilometer, I'm just thinking maybe I need to just put this in meters. So 1,000 meters is equivalent of 1 kilometer. So why don't we just call this 1,000 meters right here? How deep will the submarine be? So the depth is measured on this vertical distance here. Now remember, the submarine is now at this point here. So maybe this is point A. Now the submarine is here at point B, and this is horizontal. Maybe we'll call this point C. So we're looking to find this segment B to C. Maybe we'll call this X right here. And how will it go horizontally? So we're also looking for this horizontal distance from A to C. Right, so how far is it going along the surface of the water, and how deep is it? These are the questions. So X is on the opposite leg of 13 degrees. This is the opposite leg. And Y here is the adjacent leg. Remember, the legs make up the 90-degree angle right here. So this 1,000 right here, this is the hypotenuse. And the hypotenuse is the given side. So this means that we're going to have to use sine or cosine in this case. In fact, we're going to use both. So let's find X first. So we know that sine of some angle is the opposite leg over the hypotenuse. So I hope you see here that X is the opposite and 1,000 meters is the hypotenuse and the angle is 13. This is what we're going to use. So we got sine of 13 equals X over 1,000. 1,000 is dividing into X, and we want to undo that. So the inverse is multiply. 1,000's gone. And so now we're going to go to our calculator and we're going to put 1,000 times the sine of 13. 224.95. Let's round this. Let's say it's 225. That rounds. Those all round up. So we got 225 meters. Okay. Now let's find the adjacent leg. And in order to do that, we're going to use cosine. Cosine of an angle equals the adjacent leg over the hypotenuse. Some of you might say, oh, can we just use Pythagorean theorem because I already know the opposite is 225. And we could, but the 225 meters is rounded, and I would say always use the given values that are the exact values. So we're going to use cosine and use 13 as our angle. The adjacent is y, and our hypotenuse is 1,000. We're going to multiply 1,000 to both sides. And you'll see it's pretty much the same that we just did, except we're using a different function here. We're using cosine instead of sine. 1,000 times the cosine of 13. Okay, 974, rounding, yep, 974. So 974 meters. And the submarine problem is done. Okay, that time we did have to use sine and cosine I did say we mostly use tangent, but that problem we had to use some different ones. The other two. You are 1 mile away from SpaceX launch site in Florida, waiting for the Falcon 9 to land. You spot the Falcon making its descent and determine that it is at an angle of 80 degrees of elevation. How high is the rocket, neglecting your height, if it takes 145 seconds to land? What is the average speed? Right, in miles per hour. Okay, what we got here? You're 1 mile away. There's our distance. Okay. So we are 1 mile away. And so I don't know, I'm sure you guys have seen this rocket, right? It lands the same way as it takes off, right? And it's got a whole bunch of fire coming down here, and it's going to land right here on the landing zone, right there. There's a bullseye. And so you are a mile away, and you're looking at an angle of 80 degrees. So the angle is quite steep, right? So that angle means that that's not what I want. Let's get a different color. You are looking up from the horizon, and this angle here is 80 degrees, because that's how angles of elevation are measured from, the horizon looking up. And you know that you're 1 mile away from where it's going to land. This is 1 mile right there. And you know what? I think I'm gonna redraw this actually. I'm gonna say, because that we're looking at the bottom of the rocket here. So I'd rather, let's put it this way. And the rocket, and it's not to scale here. So the rocket is not a mile long, as it would suggest in this. So let's put it from the bottom here. So sorry, everybody. I'm going to say 80 degrees here, and this is 1 mile. And so we're looking at the bottom of the rocket, because the bottom part is the part that hits the ground, not the top, on most cases, if they're successful, right? So we want to say, how high is the rocket? Okay, and we're neglecting our height here, because, in the terms of everything here, it's quite small relative. So we're looking for that height. I hope you see here that height is opposite the 80, and the 1 mile is adjacent. So this is tangent again. Turn my stinking phone off here. So we got tangent happening again. Tangent of 80 equals h over 1, right? 1 mile. We could have put this in feet, but eventually I want to write my speed in miles per hour anyway here for my second part. So let's just go ahead and keep it. So really, the 1 here I don't even need to write. So basically, I'm just finding, well, what is the tangent of 80? And we could say 1 times the tangent of 80, right? If we multiply the 1 both sides, but I just could do tangent 80, and we get 5.67. All right, let's keep a couple of those decimals in there. 5.67, and that's miles, right? So it's 5.6 miles above the ground here. And now, if it takes 145 seconds to land, what is the average speed? So it's probably falling quite fast, and then as it gets close to the landing zone here, it really starts to decelerate and go very, very slowly until it makes a nice landing. But we're looking for the average speed. So I don't know if you've learned this in physics or physical science, but dirt, right? Dirt, D equals RT. Distance equals the rate times the time. And rate is just another way of saying speed, right? So if you think about it, if you're on the highway and you drive 60 miles and you drive for 2 hours, right? 60 times 2 is 100, and so you're driving 60 miles per hour, right? And 60 miles per hour on the highway, and you drive for 2 hours, you're going to drive 120 miles, right? That's how that works. So our distance here, we know, is 5.67, so 5.67. And the rate we don't know, right? Let's put miles here. The rate we don't know, but the time we do know is 145 seconds. 145 seconds. Okay, so if we divide 145 seconds to both sides, now I'm going to rewrite this. So I got R equals, we have 5.67 miles divided by 145 seconds. We see this is miles per second. And what does mph mean right here? It means miles per hour. So I don't want seconds in my denominator. I want hours, right? So let's get rid of seconds, and let's say, okay, we know there are 60 seconds in 1 minute, right? So that we've gotten rid of the units for seconds. So if I multiply this times 60, it will put this whole thing in miles per minute. I don't want miles per minute, I want miles per hour. So I need to now say, well, there are 60 minutes in 1 hour. I want my hour unit to be in the denominator and the minutes to cancel. So now I've got 5.67 divided by 145 times 60 times 60. And that is going to give us the average speed. Okay, so we've got 5.67 divided by 145 times 60 times 60 equals 140.77. 100, what are we doing here? How about 100, and let's just round it, 141. So our speed, average speed, is 141 miles per hour. I'm going to say mph, miles per hour. All right. And we got one left, might as well do it. Hope you guys are hanging in there. The longest zip line in the world, yes please, I want to do it, is Jabal Jais Flight, located in the mountainous desert of Ras Al Khaimah in UAE, which is the United Arab Emirates in the Middle East. Okay, so if the angle of depression from the top of the zip line is 23 degrees and the elevation change to the bottom is 3,630 feet, how long is the zip line? Okay, so we have this mountain. Okay, I'm making a mountain here, and it goes down to the horizon, and it's not quite horizontal, but that's okay. Let's say this is the horizon, and this is our, look, what can we do here? Do I like it that way? Yeah, we could do it that way. We could do it that way, I guess. Let's see. I'm going to do it like this. All right, we're on this mountain, and I'm just trying to make it cleaner for you guys. Okay, so here, the top of the zip line is right here. A, let's call this A, point A. Here we are. Let's get it in red. Top of the zip line, point A. The zip line lands down here at point B, and it takes this route, bang, right like that. And the angle of depression is 23. So remember how that works? That goes from the horizon. That's the horizon right there. Going down. This angle is 23 degrees. 23? Yep, 23 degree angle of depression from the horizon. And we want to see, we could put this in a couple places. I think I'll put it right here. Okay, I want to find what is this. I'm given this. The angle of elevation change to the bottom is this right here. So this is, let's let's get this, and maybe let's make this red right here. Okay, so that is our angle of elevation change is 3,630 feet right there. And how long is the zip line? Well, the zip line is the distance from A to B. Let's call this C. I have a right angle right here, this vertical and this horizontal line. We're looking for this hypotenuse right here. I'm going to call it X. Okay, we're looking for this length. So that is the hypotenuse and this angle right here. So we can find this angle here, or we can find this angle here. I'm going to, since I like to demonstrate our parallel line properties with the transversal, we know that this angle is also 23 because these are alternate interior angles and they're congruent. And so I got 23 degrees. I know this opposite leg over here is the angle of elevation change, and X is my hypotenuse. So this is a job for sine, because sine is the opposite leg divided by the hypotenuse. Sine of angle 23 equals 3630. That's my opposite, divided by X. Now, we saw this a lot in the previous practice. X is in the denominator, and we don't want it there. So I'm going to multiply X to both sides. Now, X is on the left side. I'll write an extra step here. X sine 23 degrees. Now, I don't want that 23 degrees to be there, sine 23 degrees. So we're going to divide it because it is multiplying times X, and we want to undo that. So we're going to divide it. Okay, so this is gone. Now X is by itself. We can put in our calculator 3630, clear, 3630 divided by sine 23. Yep. 9290. Okay, we're going to round this up. 9290. 9,290 feet. All right. So a mile is 5280, so this is over a mile long. So that is the length of the zip line. Cool, everybody. I hope you got that. I hope that all makes sense. And, good job for trying to do a lot of this on your own without me. So I appreciate your willingness to work on some challenging things. All right, have a good one.